On the 4th of January 1995, a cargo vessel called the Caledonian Star was transiting the ocean near the southern tip of Africa. A wave struck it that, by every meteorological model available at the time, should not have existed. The wave was estimated at 30 meters, roughly the height of a 10-story building. It came without the wave train that normally precedes large swells. It came, in the words of the officer who filed the report, out of nowhere and from the wrong direction. It buckled the bridge windows. It flooded the forward deck. It did not sink the ship, but it came close enough that the crew filed a report describing conditions the official meteorological record classified as moderate. Moderate, a 30-meter wave on a day the instruments called moderate. The Caledonian Star was not alone. In February of the same year, the Tasman Pioneer encountered a near-identical event in the same region. In 2001, the Norwegian cruise ship Norwegian Dawn was struck by a wave that tore off a balcony and flooded multiple cabins, again in conditions the Weather Service had not flagged as extreme. These are not folklore. They are in the incident logs, the insurance records, and the published scientific literature. They all happened in the same place, a corridor of ocean off the southeastern coast of Africa, dominated by one of the most powerful currents on Earth. This is a video about why ships still avoid that corridor, not because of a regulation, not because of a hazard label on a chart, but because of something the ocean does there that took scientists decades to explain, and that experienced sailors understood long before the equations caught up. We are going to test 4 explanations against the actual data, eliminate the ones that don't hold up, and follow the evidence wherever it goes. The Agulhas Current runs southward along the eastern coast of Africa, from the waters off Mozambique down to the southern tip of the continent. It is one of the strongest ocean currents in the world, moving roughly 70 million cubic meters of water per second. That is more than all the rivers on Earth combined, flowing through a single corridor. It is warm, it is fast. When it reaches the southern tip of Africa, it encounters the cold waters of the Southern Ocean, pushing up from Antarctica. The current doesn't simply stop, it retroflects. It turns back on itself in a series of massive eddies and loops. In the collision zone, the waves behave in ways that violate the intuitions of even experienced seafarers. Commercial shipping routes from Asia, Australia, and the Indian Ocean have historically passed through this region. The route around the Cape of Good Hope was the primary connection between Europe and Asia before the Suez Canal opened in 1869. Hundreds of vessels transit this region every month. For decades, captains have quietly, consistently routed their vessels to minimize time in the most active part of the Agulhas zone. Not because anyone told them to, but because the sea there has a reputation passed down through port briefings and pilot recommendations. The first and most obvious explanation is straightforward bad weather. The southern tip of Africa sits at the edge of the Roaring Forties, a band of latitude where westerly winds blow almost unimpeded around the globe. There are no major land masses in the southern hemisphere at these latitudes to slow the wind down. The fetch, the distance over which wind can build waves, is effectively unlimited. Waves in the Roaring Forties can reach 15 meters under ordinary storm conditions. But that explanation has a specific problem that shows up clearly in the incident data. If pure weather were the driver, the incident rate would track the weather patterns. Bad storm season, more incidents, calm period, fewer. What the data actually shows is different. The anomalous wave events do not correlate cleanly with storm intensity. The Caledonian Star incident happened on a day the Weather Service rated as moderate. The most dangerous waves in this region are not the waves that storms produce. They are the waves that appear when the storm data says they shouldn't. That is not a weather story. Weather as primary cause. Eliminated. If you're finding this interesting, hit the like button now. It genuinely helps this kind of research-heavy content reach people who want it. The second explanation is magnetic interference. The South Atlantic Anomaly is real and well documented by NASA, the European Space Agency, and multiple national geological surveys. It is a region where the Earth's magnetic field is significantly weaker than the global average. Weak enough to cause malfunctions in satellites passing overhead. Weak enough to increase radiation exposure at aircraft altitudes. The anomaly extends toward the southern tip of Africa, so it is reasonable to ask, could magnetic interference be contributing to the elevated incident rate? The answer is marginally, historically, but not as a primary driver. Modern vessels use GPS-based navigation that is largely immune to magnetic field variations. The incident rate in the Agulhas zone has not declined in the GPS era the way it would have if magnetic interference were a significant cause. A wave does not care what your compass says. Magnetic interference might complicate positioning. It does not generate dangerous sea states. Magnetic anomaly as primary cause eliminated. The third explanation is institutional avoidance driven by maritime insurance. Lloyd's of London and the broader maritime insurance market apply route-specific pricing to hull and cargo policies. Certain corridors cost more to insure than others. The Institute warranty limits define regions where additional premium is required, and the southern tip of Africa falls within a zone of heightened underwriting scrutiny. The theory runs like this: elevated incidents created higher insurance costs. Higher costs made alternative routing financially attractive. Over time, the financial nudge became a navigational norm embedded in pilot briefings and training materials. But this mechanism cannot be the primary explanation for a specific reason. Insurance pricing follows incident data. It does not precede it. The question of why the Agulhas zone generates dangerous waves in the first place is not answered by pointing to the insurance response to it. Insurance is a symptom tracker, not a cause. It tells us something real is happening. It does not tell us what that something is. Insurance pricing as primary cause. Eliminated. In 1995, the same year as the Caledonian Star, a research platform called the Draupner oil rig in the North Sea recorded a wave of 25.6 meters. Sea conditions at the time should have produced a maximum wave height of roughly 15 meters. This was the first scientifically verified rogue wave captured by instruments rather than reported by sailors. Until that moment, the scientific consensus had been that the waves sailors were reporting were exaggerations, sea stories. The Draupner measurement proved they were not. Following the Draupner event, the European Space Agency conducted a systematic satellite survey of the world's oceans. The study, known as the Max Wave Project, analyzed 3 weeks of global ocean data. It identified more than 10 individual waves exceeding 25 meters during that period alone. Under previous statistical models, waves of that size should have occurred roughly once every 10,000 years. They were occurring every few days. When the MaxWave researchers mapped the geographic distribution of these events, one region appeared with disproportionate frequency, the Agulhas Current zone. Now we can talk about why. The answer involves 3 physical mechanisms working together in a way specific to this location. The first mechanism is current-wave interaction. When a wave travels against a strong current, the current compresses the wave. The wavelength shortens, the wave height increases, the steepness increases dramatically. The Agulhas Current moves southward at speeds of up to 2.5 meters per second. The dominant swells from the Southern Ocean travel northward. The geometry is near perfect for wave compression. This is not a hypothesis, it is a measured, modeled, and documented phenomenon. The second mechanism is the retroflexion geometry. When the Agulhas current turns back on itself, it creates rotating eddies over 200 kilometers in diameter. These eddies have their own current structures and their own interaction patterns with incoming wave energy. A wave compressed by the main current can then encounter the edge of one of these eddies moving in yet another direction. Multiple wave trains from different directions arrive at a single point simultaneously and constructively interfere with each other. This is why the wave comes from the wrong direction. It doesn't come from where the wind is, it comes from the geometry of the current system underneath. The third mechanism is bathymetric focusing. The seafloor beneath the Agulhas zone is not flat. The Agulhas bank, the shallow continental shelf extending south from South Africa, creates a sharp transition between shallow and deep water at its edge. When wave energy moves from deep water to shallow water, it slows down and compresses, the same way light bends moving from air into glass. This refraction focuses wave energy from a wide area into a narrow corridor, concentrating and intensifying it. The specific bathymetry of the Agulhas bank edge has been mapped in sufficient detail to show certain areas are particularly effective at focusing incoming wave energy. These areas correspond closely to where rogue wave incidents have been reported most frequently. 3 mechanisms, each real, each documented, each insufficient alone, but together they create conditions where extreme wave events are orders of magnitude more likely than the global baseline. This is why the forecast can say moderate and a 30-meter wave can still appear. The wave is not produced by the local weather. It is produced by the interaction of current, geometry, and seafloor, independently of what the atmosphere is doing overhead. This is what the captains knew before the scientists did, not in these terms, not with this vocabulary, but in the way experienced seafarers accumulate knowledge through incident reports, through other officers' stories, through the feel of water doing something the instruments aren't capturing. The Agulhas zone had a reputation long before it had an explanation, and the reputation, it turns out, was accurate. After the MaxWave project, the International Maritime Organization began incorporating rogue wave risk into vessel design standards. Classification societies updated structural requirements for ships operating in high-risk zones. Routing software began including current interaction models in its optimization algorithms. The knowledge sailors had carried informally for generations was systematized, quantified, and embedded in the infrastructure of the industry. The route adjustments captains had been making by instinct became route adjustments the software recommended by calculation. The destination was the same. There is a tendency to treat the moment of formal verification as the moment something becomes real. For the Draupner measurement, rogue waves were not real in the scientific sense, even though sailors had been reporting them for centuries. After the Draupner measurement, they were. The waves did not change. The ocean did not change. What changed was the availability of a form of evidence that the scientific framework recognized as legitimate. The gap between a thing being real and a thing being formally verified can be very long. During that gap, the people closest to the phenomenon, the people whose lives depend on reading it correctly, are often doing exactly that, reading it correctly, without the equations. The captains who routed around the worst of the Agulhas zone were not being superstitious. They were being rational in the deepest sense of the word, responding to evidence their instruments and theoretical frameworks hadn't yet found a way to capture. They were performing empirical risk assessment based on observational data. They just called it seamanship. How many other places on Earth carry that same kind of accumulated, inarticulate, experientially verified knowledge? How many other corridors, passes, and stretches of water have a reputation that the official record hasn't caught up with yet? And what would it mean to treat that reputation as a hypothesis worth testing rather than a superstition worth correcting? If questions like that are why you watch this kind of content, The subscribe button exists for exactly this reason. Leave a comment with what you thought the explanation was going to be before we got to the current interaction physics. I read every one of them. The pattern in what people predict versus what the evidence shows is its own kind of data. I'll see you in the next one, placeholder.